this video we're going to go over matrices. We're going to go over adding, subtracting, multiplying, dividing matrices together. So we're going to start off with adding and subtracting. When you're adding and subtracting matrices, the two matrices have to have the same number of rows and the same number of columns. So if you see here, both of these matrices have the same number of rows and the same number of columns, which means you can add them. When you add them, you add the number that's in the same position on the other matrix. So 3 plus 7, 10. Then you have 7 and 9, 2 and 6, and 1 and 5. And that's it. So as long as the dimensions of the matrices are the same, you can add them. For subtracting them, it's the exact same thing. You need the dimensions of the matrices to be the same, and you just minus the numbers that are in the same position. So 3 minus 5, 9 minus 2, 7 minus 1, 2 minus 3, 6 minus 9, and 1 minus 8. I should also mention, when adding and subtracting matrices, the answer has the same dimensions as the of the things you're adding. So the dimensions are 2 by 2 and the dimensions are 3 by 2. It's row first and then column. So 3 rows and 2 columns. So now we'll move on to multiplying. When you multiply matrices, the number of columns of the first matrix must be equal to the number of rows in the second matrix. So in this example, we have a 2 by 2 and a 2 by 1. So a quick way to identify some of the properties are, if you draw the dimensions, the inner numbers must be equal, right? So this is the number of columns and the number of rows. Basically what this says. And in order to multiply them, these two inner numbers must be equal. The outer numbers give you the dimensions of the answer. So if we do this multiplication, you basically multiply the columns across the rows. So if we do it slowly, so the way you would multiply this is 60 times 4 plus 5 times 2. And then it will be 9 times 4 plus 25 times 2. Right? And then if we do all those sums, we get 60 times 4, 240, plus 10, 250, plus 36 plus 50, which is 86, right? And that's the answer to the multiplication. You can see here, we proposed the dimensions of the answer to be 2 by 1, and the answer has 2 rows and 1 column. So the dimensions of that answer is 2 by 1, which is correct. If we do a couple more of these examples, so here we've got a 2 by 2 for both of them. We know the answer is going to be a 2 by 2, and we know we can multiply it because the number of columns equals the number of rows, right? So if we start, we've got 4 times 2, which is 8, 4 times 2 plus 1, and then we have 2 times minus 1, which is minus 2, plus 2, 4 times minus 2, plus 3, and 2, plus 6. So we add all these up. 9, 0, -5, and 8. 2 by 2. So basically the multiplication is you go across each row in each column to generate the answer. We'll do it for the next one. So we'll do 4 times 2 plus 2, 4 times 1 plus -3, 2 times 1 plus -4, and 1 plus 6. And then we sum everything up. We have 10, 1, -2, and 7. This next one. So we can write the dimensions to see if we can multiply them. We have 1, 2, 3, 3 rows and 2 columns. And this one we have 2 rows and 3 columns. Right. So we can see here the inner two numbers match. That means we can multiply them. And then from the outer two numbers, they're going to be the dimensions of our answer. So it's going to be a 3 by 3. So if we go ahead, so 0 times 1 is 0, plus 2 times 2, and then we do 0 times 2, which is 0, plus 2 times 3, which is 6, and then we have 0 times 1, which is 0, 2 times 1, which is 2, 2 times 1, 2, plus 2 times 1, 2 times 2, plus 1 times 3, 2 times 1, plus 1, 1, plus 6, 2, plus 9, 1, plus 3. So once we've added all that up, we get 4, 6, 2, 4, 7, 3, 7, 11, 4. That's our answer. 3 by 3 matrix as well. Yep. So to divide a matrix, you multiply by the inverse, and the inverse is shown by this little a to the -1. So a formula to get the inverse is to use the determinant, which we can work out later, and to change the matrix as well. So say we had a matrix PQRS. In order to get the inverse, we need to switch around P and S, so they switch places, and R and Q are negated, as in you put a negative sign in front of it. For the determinant, there's this formula we can use to calculate it. If we do the example with this matrix A, so first of all we need the determinant, because it's 1 over the determinant. To get the determinant, you do PS minus RQ. So we have here PS minus RQ. These relate to the positions in the matrix, like where P is, i.e. top left, and so on. So we calculate the determinant, PS minus RQ. So 1 times 2, which is 2, minus RQ, which is -1 times 3. -1 times 3 is -3. So the determinant is this. We can simplify it later. And then for this portion, we swap S and P and we negate R and Q. So swap S and P, we have 2 and 1. See how we swap those positions? And then we negate these two. So we have 1 and -3. If we simplify a bit further, we can do 1 over 2 minus minus, which is a plus. So 1 over 5 times 2 minus 3, 1 and 1. And that's it. We can multiply out the brackets, but all of them would just be over 5. So, and that's the inverse of this matrix here. So a matrix multiplied by its inverse will result in the identity matrix. In numbers, it's like multiplying a number by 1 over that number, because the numbers cancel out, so you'll get 1. We can do it with these examples. If you multiplied, say, a by this value, you would get the identity matrix. I could do an example here. So if you did 1, 3, minus 1 and 2, multiplied, say we multiplied 1 over 5 by all of them. So we had 2 over 5, minus 3 over 5, 1 over 5, and 1 over 5. We learned how to do matrix multiplication on the other sheet. So if we do that here, we have 2 over 5 plus 3 over 5, right? Because we've done 1 times 2 over 5 and 3 times 1 over 5. Now we do 1 times minus 3 over 5, which is minus 3 over 5, plus 3 over 5. And then we do minus 2 over 5, plus 2 over 5. Then we have minus minus, so plus, so 3 over 5, and 2 over 5. So an identity matrix is basically where you have ones from left to right, up to down, in a diagonal formation, and the rest of the values are 0. So this will result in an identity matrix. 2 over 5 plus 1 over 5 is 1, right? Because the denominators are the same. So 2 plus 3 is 5, 5 over 5 is 1. Minus 3 over 5 plus 3 over 5, 0. Minus 2 over 5 plus 2 over 5, 0. 3 over 5 plus 2 over 5, same again, 1. So as I said, it's left to right, top to bottom, 1s, and the rest are 0s. Another example of an identity matrix is, right, you have a diagonal set of 1s, and this can go if you have 4, 5, 6, 7, whatever. The rows and the columns are the same, and you just have 1s on a diagonal. For a 3 by 3 matrix, so you have 3 rows and 3 columns, you might be asked to find the determinant. So we have another formula for a 3 by 3. It's a little bit more complex, but all in all, just simple multiplication. So with this example, we're going to find the determinant. So we start off with 1 multiplied by these two values. 1 times minus 1 is minus 1, minus 3 times 1, which is 3. And then we have minus 2. And then we do 4 times 1, minus 0 times 1, which is 0. And then we do plus 3, 4 times 3, minus 0 times minus 1 is 0. So if we neaten that up a bit, 1 minus 1 minus 0, minus 1 minus 3, sorry, is minus 4, minus 2, 4 plus 3, 12. Multiply out, minus 4, minus 8, plus 36. And then if we add all that together, we have minus 12, 24. Right, and that's the The method to find the inverse of a 3 by 3 matrix is to use Gaussian elimination. This is where you append an identity matrix on the right and then you rearrange the rows so that the left side has the identity matrix and the right side would show the inverse. So if we start with this example, we can minus row 3 from row 2. So row 1 stays the same. So row 3 minus row 2, we have 0, minus 1, minus 1, so 0, because it's minus 1 plus 1. 1 minus 0, 0 minus 0, 0 minus 1, 1 minus 0. And row 2 stays the same. Now we can minus row 2 from row 1, because we want to get a 0 here, right? For the identity matrix we want a 0. So we have row 1 the same, we have row 3 the same. So row 2 minus row 1, so 1 minus 1 is 0, minus 1 minus 0 is minus 1, 0 minus 1, 0 minus 1, 1 minus 0, and 0 minus 0. So now if we multiply row 2 by minus 1, we can get this to equal 1. Row 2 times minus 1, 0 minus 1, 1 0 0, 0 1 minus 1, 1 minus 1 0, 0 0 1 0 minus 1 0. So now if we add row 3 to row 1 and row 2, we can make both of these equal 0, and then we'll have our identity matrix. So row 3 added to row 1 and row 3 plus row 2. So if we do that, we still have the same row 3. Now row 1 is going to be added to row 3. So 1 plus 0 is 1, 0 plus 0 is 0, minus 1 plus 1, 1 plus 0, 1 minus 1, 1, 0 plus 1. Now row 2 is also going to be added to row 3. So 0 plus 0, 1 plus 0, minus 1 plus 1 is 0. 1 plus 0, minus 1 plus minus 1, so it is minus 2. 1 plus 1, 0 plus 1 is 1. So that's the inverse of the matrix that we had up here. And you can prove it's the inverse by multiplying the original matrix, which is A, by the matrix inverse we've just worked out. So if we multiply that, we get 1 plus 0 plus 0 minus 1, which is plus 0 plus 1, 1 plus 0 minus 1, 1 minus 1 plus 0 minus 1 plus 2 plus 0, 1 minus 1 plus 0, 1 minus 1 plus 0 minus 1 plus 2 minus 1, 1 minus 1 plus 1. Then if we summarise that up, we have 1, 0, 0, 0, 1, 0, 0, 1, oh no, 0, sorry, and 1. That's the identity matrix. So we've proved that this is the inverse using Gaussian elimination, and that's it.